homework 4.2, which is where a lot of problems stem from. You have h of t was equal to 4e to the negative 2t cosine 3t u of t, and x of t was e to the negative t u of t. Am I remembering that correctly? Okay. And so one of the, it's not a mistake technically, but one of the things that I see you guys doing, which will make your life infinitely harder on yourselves, is you're always applying the t to the minus tau substitution to h of t. But the properties of the convolutions tell us that we can do it to either of the functions. And from a mathematical standpoint, it'll be way easier if you do the t minus tau substitution on this guy as opposed to this guy, right? So I would expect you guys to do the integral from 0 to t of 4e to the negative 2 tau cosine 3 tau multiplied by e to the negative t minus tau d tau, which you can then simplify to 4e to the negative t integral from 0 to t of e to the negative tau cosine 3 tau d tau. And then this is practically the same integration by parts that we worked in the class example. Nothing particularly wild or crazy about it. Brody, what up?
So all these problems, when you set up the interval, you're just kind of like disregarding the function or just plugging it in.
So let's talk about that, okay? So if we wanted to be more formal about things here, we would also have a u of tau and a u of t minus tau, and then a d tau. Okay? So we are integrating with respect to tau from 0 to t, which means we are looking at instances where tau is between 0 and t. And we have the instance where tau is equal to 0, bounding on one side, and the instance where tau is equal to t, bounded on the other side, right? So u of tau is always going to look like 1 because 0 is included in our limits of integration, right? So when tau is exactly equal to 0 or any number greater than 0, this guy fires off to be 1. For this guy right here, t minus tau is always a positive quantity if we are restricting tau to be between 0 and t, which means this guy is also always going to look like 1 over our interval. So the reason that we throw them away is because they both represent the number 1.
But then we just add the unit stuff.
So the unit step at the end there is taking into account where this thing effectively, I don't want to call it lives or whatever, but like we know that this function is causal. So it has a 0 value for t less than 0. This function is also causal, so it has a 0 value for t less than 0. So what means is that when I multiply these guys together, effectively, it's going to be 0 until t is equal to 0, at which case these things turn on. So I can just take my results from this and multiply by a factor of a unit step function to imply that it's 0 before t is equal to 0. In the later problems where we're doing the convolution and it has, it behaves a certain way over a specific interval, I'm just using those unit step functions to as an alternative way to write a piecewise function effectively, but it's doing effectively the same thing. Did that clear that up? Okay. So this is how you would handle homework for problem 2. if you don't want to suffer through things. A possible way to do it, if you were just really gung-ho about doing the t minus tau substitution of this guy, would be to use Euler's identity to express the cosine function as a sum of exponential functions, because then you're just multiplying exponential functions together, and that's less of a pain in the ass than dealing with a time-shifted cosine function. So that would be a way that you could do it. Doing the t minus tau substitution for h of t without just having to suffer through a ridiculous amount of math. So it'd be more setup, and then the calculus part of it would be fairly straightforward. All right, so homework 4.2. Any questions about this setup? And then from this point, it's just crap you've done in your math classes before. All right, homework 4.4. So in this particular problem, we have x of t is something like this, right? Where we have a constant value of 2 over the interval from 0 to 1, and then it linearly decreases from 1 to 2. And we could mathematically represent this part as negative 1/2, because the slope is negative 1/2, right? Or no, yeah, hold on. It changes 2 in 1. So nope, the slope is negative 2, my bad. And like me, we need to fix it because when I did on the board, I used the wrong slope. T minus 1, because it's time shifted 1 unit to the right, plus an intercept of 2. So what I'm expecting to have happen is that t is equal to 1. This function should have a value of 2, and at t is equal to 2, it should have a value of 0. So negative 2 times 1 plus positive 2 is equal to 0. So this mathematically describes what's going on there. I use this time shifting thing because I'm too lazy to figure out what the intercept would have been at actual t is equal to 0. So I just shift it by 1 unit to the right and then figure out what value it has at 1 unit to the right to do the slope intercept format, because I'm very lazy. So our h of t function is an exponential. Imagine I can draw an exponential. 3e to the negative t u of t, I think. Am I remembering correctly? So for this particular problem, and I'm pointing this out explicitly because somebody asked me about it, I believe that it is significantly easier to set things up if we flip and slide this one versus flipping and sliding this one. Yes, ma'am. So I think it's -2 because the change in the y value is -2 over a change in the x value of 1. So when we were in my office, I accidentally did this backwards. It should be -2 and not -1. So there are going to be 3 intervals here, right? So we're going to have 4 t is less than 0. And so for t is less than 0, this is our tau axis. So our piecewise function is still going to look like this. And then our exponential function is going to look like this. There's obviously no overlap, so the result of this convolution or this part should be 0, right? For 0 is less than t is less than 1, we're obviously going to have something here, right? So y of t will be the integral from 0 to t of 2, which is a contribution of the blue curve because it has a fixed value. And then we're going to have 3e to the negative t minus tau d tau, and then I'll leave it up to you guys to actually do that calculus. Then we have the region where 1 is less than t is less than 2. Obviously, there is overlap. So this is going to look like the integral from 0 to 1 of 2 times 3e to the negative t minus tau d tau plus the integral from 1 to t of negative 2 times t minus 1 plus 2 multiplied by 3e to the negative t minus tau, excuse me, d tau. Does that make sense? And then we have for t greater than 2.
Yeah, tau minus 1.
Yes, thank you. Because I should be, yeah, you're 100% right. Thank you there, Ben. Because that would make a big difference if we're treating it as a constant or a variable when it should be a variable there. So I appreciate the catch. So here we're going to have the integral from 0 to 1 of 2 times 3 to the e to the negative t minus tau d tau plus the integral from 1 to 2 of negative 2 times tau minus 1 plus 2 times 3e to the negative t minus tau d tau. We don't need to worry about anything past 2 because our blue function is 0 for all t past 2. So that's why our integration effectively stops at t is equal to 2. And math that up, put the results together, and call it a day. So just to explain why I think this is the better route for doing this, let's look just really quickly at what would happen if we flipped and slid the other thing, right? So here's tau. Here's our this guy. And then let's just say for the sake of argument that this is the interval that we're looking at. The problem that we would have here, in my opinion, is how do we define this line when we're moving it in time so that the intercept also changes as a function of time. I would argue that's really, really hard to do. So to avoid that, flip and slide the exponential function. Because for this region, so like if this was t right here, then this would be t minus 1. So from t minus 1 to t, things are going to be pretty. But from t minus 2 to t minus 1, things are going to be a little bit harder to describe what's going on in there. So, just my 2 cents. Yes.
As a general rule of thumb, would you recommend flipping and shifting as much as
I would recommend flipping and shifting the one that's easier to mathematically describe. Because to me, my brain doesn't get as terrified if I'm not making something really complicated, which is exactly why in this problem, I chose to flip and slide this guy, because that's an easier substitution to make. Figuring out what the hell is going on when I have 3 to the t minus tau and how to take that into account when I'm doing all that integration by parts scares me to death. So I don't want to do it. So it can be done, I'm sure. If you go talk to somebody in the math department, I bet they'd say it's easy. Talking to somebody in the engineering department, they're going to say why when you could do it this other way. So, all right. So, any other questions about homework set number 4? I am going to extend the due date by 1 day. I do want to remind you, it's still on the test on Friday, so you still need to know how to do this. I wouldn't expect anything as difficult as either of these 2 problems on the exam. I'm going to try to make it to where you don't have to do any kind of integration by parts. I can't guarantee that, but if you do have to do integration by parts, it's going to be something real dumb and easy. Okay. Yeah. So, like I said, any questions about this, or can we talk about Laplace transform something? Laplace, yeah. Okay. So today we are just going to talk about properties of the Laplace transform. Some of these we have already touched on briefly, but we're going to go through them again just to really hammer it home. So in our last class meeting, we defined the Laplace transform and the inverse Laplace transform. And we worked a couple of simple examples. So I think we worked one for a unit step function, or we could apply it to a unit step function. I think it was just a rectangular pulse, stuff like that. We also looked at an exponential function and then used the exponential function to derive relationships for cosine functions without a phase angle, sine functions without a phase angle, and then put those together to understand what was going to happen for a cosine function that also had a phase angle and a sine function that also had a phase angle. There are other things that we are going to, signals that we see relatively regularly-ish, that using just those relationships that we developed in the last class meeting would be difficult. So for example, let's say that I had an underdamped system and the capacitor voltage was of the form B1 cosine omega dt plus B2 sine omega dt, this whole thing multiplied by e to the negative alpha t. And then we might also have some initial condition. Right? This is just an example. We're not even going to do this right now. If we tried to use the results from our last class meeting, like we know how this cosine omega dt bit is supposed to behave. We know how to do the Laplace transform of this part. Multiplying it by a scalar is just multiplying the Laplace version by a scalar. We know how to do this part, multiplying it by B2 is easy, but we don't know how to do a sine function multiplied by an exponential function, right? We could suffer through a bunch of things and figure it out, or we can utilize the properties of the Laplace transform to make it kind of trivial, because if we know what this is, and we understand that this is technically a frequency shift function, we can come out with the result with just using what we already know, and then understanding these properties, okay? So the first property that I want to talk about is the linearity property, okay? And this one we kind of already dealt with, okay? So what did linearity look like back in circuits 1? For those of you that had me, right? So we said something to the effect of, if you have a system that has an input x1 and an input x2, if you scale input x1 by a certain amount and scale input x2 by a certain amount, the output will look like the output response y1 scaled by the amount that x1 was scaled by, plus the output response y2 scaled by whatever input x2 was scaled by, added together, right? So we talked about the superposition theorem or the additivity theorem, and then we also talked about the homogeneity or scaling theorem. Laplace transform obeys the exact same rules, okay? So if we have a generic function f of t that could be expressed as k1 times some function f1 plus k2 times some function f2, the Laplace transform of this is going to be k1 times f1 of s plus k2 times f2 of s. So we see the additivity property and the scaling property buried in as well, okay? Proving this is pretty straightforward. So if I want the Laplace transform of k1 times f1 of t plus k2 times f2 of t, that is going to be the integral from 0 minus to infinity of k1 f1 of t plus k2 f2 of t e to the negative st dt by definition. Since I have two discrete functions, I can split this integral up into two integrals. That's going to look like the integral from 0 minus to infinity of k1 f1 of t e to the negative st dt plus the integral from 0 minus to infinity of k2 f2 of t e to the negative st dt. Since those k's are constants, that's going to look like k1 times the integral from 0 minus to infinity of f1 e to the negative st dt plus k2 times the integral from 0 minus to infinity of f2 e to the minus st dt. And then this is just simply k1 times f1 of s plus k2 times f2 of s, because the integral from 0 to infinity of f of t e to the negative st is literally the definition of the Laplace transform. Okay. So the Laplace transform is inherently a linear operation, which means it should be applicable to any linear circuit that we encounter, which is great news. The second property that I want to look at is the time scaling property. So the time scaling property is as follows. If we have a function where our variable is scaled by a factor, right? So think of scaling by positive a as stretching the time axis. Our Laplace transform is going to look like 1 over a times f of s over a. So if we stretch the time axis, we compress the frequency axis and vice versa. And we also reduce the magnitude of our Laplace transform by the same amount as we stretch the time axis effectively. So once again, let's prove it. So the Laplace transform of f of at is going to be the integral from 0 minus to infinity f at times e to the negative st dt. So I'm going to introduce a dummy variable here. So let's say that tau is going to represent the quantity a multiplied by t. Well, if we take the derivative of this guy, what we're going to find is that dt will be 1 over a times d tau. So substituting these in, our integral is going to look like 0 to negative infinity of 1 over a f of tau times e to the negative s over a times tau d tau. Let's call x s over a. So that our integral now looks like 1 over a times the integral from 0, sorry, I have 0 to negative infinity. It should have been 0 minus to positive infinity. So sorry about that. F of tau e to the negative x tau d tau. What does everything except 1 over a here look like? the definition of the Laplace transform, except that S has been replaced by X, right? So that's going to look like 1 over A times F, capital F of X, which is the same thing as 1 over A times F of S over A, right? So stretching in time results in a compression in frequency as well as a reduction in magnitude. Compressing in time means that we're going to stretch in frequency and amplify our signal. So effectively, that's just if A is greater than 1, we're stretching time and compressing frequency. If A is less than 1, we are compressing time and stretching the frequency limit. Our third property, we'll go to, I'll start on this page. Is time shifting. So we stumbled into this one when we dealt with our, sorry, that should be capital T, rectangular pulse waveform on Monday, right? So the Laplace transform of a function that is time shifted is just the Laplace transform of the non-shifted function multiplied by a factor of t to the negative capital T, where that's the amount we've shifted, times S. We have to constrain capital T, our time shift, to be a positive quantity because a shift to the right would result in a non-causal system. And that's going to mess with our limits of integration and all that kind of stuff that we've defined. Okay. So proving this fairly straightforward. The Laplace transform of f of t minus capital T u of t minus capital T is going to look like the integral from 0 minus to infinity of f of t minus capital T u of t minus capital T. I got so used to writing tau's that I can't stop. E to the negative st dt. Once again, we're going to say that our unit step function is going to look like 1 over our interval of interest because we're dealing with a causal system. So I'm going to put equals to the integral from capital T to infinity, right? So just like we dealt with the ramp function, everything up until we hit time t is going to be 0 multiplying by this function. Everything by that function. We get f of t minus tau, excuse me, t minus capital T, can't stop saying it, e to the negative st, and let's say that x is t minus capital T, and dt will then be the same thing as dx. Substituting in these relationships, we get the integral from t to infinity of f of x times e to the negative s times x plus capital T dx. Are we okay with that substitution? So x plus t will be equal to lowercase t. And now I can factor out an e to the negative s capital T and move it outside of the integral. And we are left with f of s e to the negative e times s. So effectively, a shift in time by some amount capital T means that we simply multiply our Laplace transform by a factor of e to the negative capital T times s. What we're about to look at is the frequency shifting property, which is effectively the exact same thing, but in the opposite direction. So if we shift our frequency by some amount a, it's multiplying our time domain function by e to the negative a t. So e to the negative alpha t, or let's call it a, because I've been using a, e to the negative at f of t has a Laplace transform of f to the s plus a, right? So this is a frequency shift, which results in the multiplication of our time domain function by e to the negative shift times the variable in the time domain. So it's the exact same relationship that we just had for a time shift, but in the opposite direction. Right? So the Laplace transform of e to the negative at f of t is equal to the integral from 0 minus to infinity f of t e to the negative at times e to the negative st dt, which will be the integral from 0 minus to infinity f of t e to the negative s plus a t dt, or simply f of s plus a. So before we look at the other couple of properties here, scrolling all the way back to the beginning, we can now pretty easily understand how to do the Laplace transform of this function just using that previous property and what we developed in class the other day, right? So just as a quick aside here, we know that for f of t is equal to cosine omega t, f of s was s over s squared plus omega squared. Am I remembering that correctly? For f of t was sine of omega t. F of s was omega over s squared plus omega squared, right? So if we have this guy, then our Laplace transform should be s plus A over S plus A squared plus omega squared plus omega over S plus A squared plus omega squared. No actual work needs to be done, right? Doing that the long way would be quite a pain in the ass. Understanding what frequency shifting means makes it trivial, right? So that's why learning what these properties mean and how to apply them can be so important, because you can make a very daunting looking waveform have an incredibly easy to determine transform. All right, so property number 5 will be time differentiation. And this is actually something that we kind of saw way back in circuits 1. We just didn't necessarily realize it. So let me explain what I mean by that. Way back when we were developing our phasor relationships and all of that kind of stuff, and we were trying to figure out what the phasor relationships were for inductors and capacitors, we found that taking the derivative in the time domain was the same as multiplying by j omega in the frequency domain. So our complex frequency, S, is just sigma plus j omega. So it stands to reason, based on our prior history and understanding of things, that a derivative in the time domain will be just multiplying by S in the frequency domain. We'll prove that here. So if I have the derivative of a function in the time domain, its Laplace transform will be S times f of S minus f evaluated at 0 minus. So we're going to include initial conditions here, right? Which is going to work great for capacitors and inductors because they have initial conditions. Right? We're slowly tying this back to actual circuit analysis. Okay. So proving this, the Laplace transform of the derivative of f of t with respect to time will be the integral from 0 minus to infinity of the derivative of f of t with respect to time, e to the negative st dt. I'm going to do integration by parts here. So let's say that u is e to the negative st. U prime, I think that's the notation that I've been using, would be negative s e to the negative st. V prime will be the derivative of f with respect to time, which means v should just be f as a function of time. Excuse me. So using integration by parts, we're going to have u times v, so that is f of t e to the negative st evaluated at 0 minus and infinity minus the integral from 0 minus to infinity of u prime times v. So that's going to be negative s f of t e to the negative st dt. Right? So at t is equal to infinity, this bit right here goes to 0. So we're going to have 0 minus f of 0 minus. So negative f of 0 minus, which is our initial condition, plus s times the integral from 0 minus to infinity, f of t e to the negative st dt. Rearranging this ever so slightly, we have s times f of s minus f evaluated at 0 minus. So the derivative in the time domain is just multiplication by s in the frequency. We can generalize this for further derivatives by just doing this process over and over and over again. So effectively, how it works is the derivative, let's call it the nth derivative of our function f of t, will have a Laplace transform of s to the nth power times f of s minus s to the n minus 1th power of f of 0 minus s to the n minus 2 power of the derivative of f t evaluated at t is equal to 0 minus all the way out to s to the 0. So effectively, when we just wind up with 1, the derivative to the n minus 1th power of f of t dt to the n minus 1 evaluated at t is equal to 0. Now, realistically, I think the only thing that we would ever have to particularly deal with besides first derivatives might be second or third derivatives. We know that we had second order differential equations when we were looking at RLC networks and all that kind of good stuff. If you had other energy storage elements, you could get higher order equations and all that kind of good stuff if you wanted to. But for the most part, only the first and second derivative relationships are things that we're going to use standard.
So you left that upper bound and take the.
What upper bound?
At in mind, yeah. Like, you just put E with your line.
No, so this isn't an integral. This is evaluating this derivative at t is equal to 0 minus. This is evaluating the derivative at t is equal to 0 minus. So like in a textbook, you would probably see this as f dot of 0 minus and f, either dots or primes, and I don't like that notation because I find it confusing. So this means find the derivative of the function, evaluate that derivative at t is equal to 0 minus. Thank you for that. All right, so this is time derivation or time differentiation. Technically speaking, there's also a frequency differentiation property of the Laplace transform as well. We will never actually practically use it, but if taking the derivative with respect to time results in multiplying by s in the frequency domain, taking the derivative with respect to s results in multiplying by negative time in the time domain. So it's just your function negative times negative 2, but we won't actually ever use that thing. So the duality of this stuff's pretty great. All right, time integration. So time integration property of the Laplace transform says that the integral from from 0 minus to infinity of a function f of tau d tau is just 1 over s times f of s. So if taking the derivative in the time domain results in multiplying by s, taking the integral in the time domain is dividing by s, effectively. Okay. And once again, we'll prove it. So the Laplace transform of the integral from 0 minus to infinity of f of tau d tau is the integral from 0 minus to infinity of, sorry, I need to change these limits here. My apologies. This should be from 0 to t. Sorry about that. F of tau d tau e to the negative st dt. We're going to do integration by parts again. So u is going to be the integral from 0 to t of f of tau d tau. U prime is then just f of tau. V prime is e to the negative st, and v is negative 1 over s e to the negative st. So what we're going to get is, so let's see here. So I'm going to have u times v. This negative 1 over s bit is going to be a constant term. So I'm going to pull that outside of the integration, right? So I'm going to have negative 1 over s e to the negative st times the integral from 0 minus to t of f of tau d tau. This whole thing evaluated at infinity and 0 minus the integral of u prime times v. So this is going to be the integral from 0 to infinity of negative 1 over s ft e to the negative st dt. All right. So when t is equal to infinity, what does this term go to? 0. So the exponential function goes to 0 when t is equal to infinity. So 0 times whatever this integral is looks like 0. What happens when t is equal to 0 minus? Well, this bit's going to look like 1. But what's the integral from 0 minus to 0 minus of a function? 0, because there's no area under the curve because there's no distance that we're integrating in, right? So this whole part right here just goes to 0. So that's going to leave us with negative times negative is going to be positive. I'm going to pull the 1 over s out because it's a constant term. Integral from 0 minus to infinity f of t e to the negative st dt, where that integral is the definition of the Laplace transform. So we have 1 over s times f of s. Yes, Gabriel. Okay, let's change all the t's to tau. What difference does it make? Tau is just a dummy variable for t, so they both represent time, so it literally doesn't matter. Yes. It should be 0 minus for everything. So let me go back and fix this. So just to be clear, the reason why we use zero minus instead of just zero is because we want to be able to take into account any initial conditions on stored energy in capacitors. For just this mathematical derivation stuff, it really doesn't particularly matter. But once we get into circuit analysis, it will. So thank you for that, and I apologize for missing a few of the minuses. All right, so the last property that I want to talk about is the greatest property in the world, and you guys will probably agree here in just a moment, and it is the time convolution property of the Laplace transform. Yeah. So the time convolution property is, is as follows. If we have a function f1 of t convolved with a function f2 of t, the Laplace transform of this convolution is simply f1 of s multiplied by f2 of s, meaning convolution in the time domain is simply multiplication in the frequency domain, which means if we can find the Laplace transform of our signals and our impulse response, we never have to do convolution again. We can simply multiply their Laplace transforms, take the inverse transform, the inverse Laplace transform to get the result of that convolution in the time domain. This one's pretty damn great. So last thing we're going to do here is once again prove why it works. So the Laplace transform of f1 of t convolved with f2 of t is the integral from 0 minus to infinity of the integral from 0 minus to infinity of f1 of tau times f2 of t minus tau d tau times e to the negative st dt. Just doing a simple substitution here. We're going to define u to be t minus tau, and du will be the same thing as dt. So, making this substitution, our integral is going to look like the integral from 0 minus to infinity of the integral from 0 minus to infinity of f1 of tau times f2 of u d tau e to the negative hold on, what did s of u plus tau. Almost skipped the step that would have been quite confusing. The u. Yes, James. So let's see here. So tau is ranging from 0 to infinity. I understand where you're coming from, but because we're integrating from 0 to infinity on both things, I don't think it's going to change people. That makes sense. Because t is being integrated from 0 to infinity. And so when we go from 0, we're still going to be going from 0 to infinity. So I'm not 100% sure, but I'm going to leave stuff as is, because the math is gonna work out if I leave it this way. All right, so what I'm gonna do now is I'm going to rearrange these integrals, okay? So I'm gonna have the integral from 0 minus to infinity of f1 of tau e to the negative s tau d tau. So I'm splitting this exponential up into two things. One is going to be e to the negative s times tau. The other one is going to be e to the negative s times u. Times the integral from 0 minus to infinity of f2 of u e to the negative su du, which is just the Laplace transform of our first function multiplied by the Laplace transform of our second function. So this is the proof for the convolution property. You don't have to understand it. I'm not going to say that I fully do, but we're going to use the bejesus out of this. Because as you guys have noticed, actually doing convolution integrals tends to be miserable. So we're going to avoid it if at all possible, and simply find the Laplace transforms, multiply them in the frequency domain, take the inverse Laplace transform, call it the Gabriel. For the exam on Friday, you cannot use the Laplace transform for anything. I explicitly want you to evaluate the convolution integrals. Beyond Friday's test, yay, boo, hiss, I'm a jerk, whatever. Beyond Friday's exam, the expectation will be that you'll use Laplace transforms for everything. So the test on Friday, I explicitly want you to do convolution integrals. I don't know how more clear about that I can be.